Welcome! In this session, we'll explore problem number 891, sum of subsequence widths. Together, we'll break down the problem, understand its requirements, and analyze potential approaches to solve it. Let's dive in. In this problem, we need to calculate the sum of the widths of all subsequences of a given integer array nums. First, let's define what we mean by the width of a subsequence. The width is simply the difference between the maximum and minimum elements in that subsequence. For example, if the subsequence is 2, 5, 7, the width would be 7, 2 equals 5. Our task is to compute the sum of these widths for all possible subsequences of the array. However, since the total number of subsequences can grow exponentially as the size of the array increases, the result can become very large. To handle this, we are instructed to return the sum modulo 10 to the power of 9 plus 7. Additionally, it's important to note that a subsequence is derived by removing some or no elements from the array while maintaining the order of the remaining elements. For the input, we're given an integer array nums of length n, where n is between 1 and 2000, and each element of nums is between 1 and 10 to the power of 6. The output will be a single integer representing the modulo result of the sum of widths of all subsequences. Let's consider an example to make this clearer. Suppose the input array is nums equals 2, 1, 3. The subsequences of this array include all possible combinations of its elements, like 2, 1, 3, 2, 1, 2, 3, 1, 3, and 2, 1, 3, along with the empty subsequence. For each of these, we calculate the width, which is the difference between the maximum and minimum values. For instance, the width of 2, 1 is 2, 1 equals 1, and the width of 2, 1, 3 is 3, 1 equals 2. Adding up the widths for all subsequences, we get 0 plus 0 plus 0 plus 0 plus 1 plus 1 plus 2 equals 6. Therefore, the output for this example is 6. Now, let's look at another example with nums equals 1, 2, 3, 4. Here, the subsequences include combinations such as 1, 2, 1, 4, 2, 3, 4, and so on. For each subsequence, the width is calculated as the difference between the maximum and minimum values. When we sum up the widths of all subsequences, the total is 50. However, calculating the widths for every subsequence directly is impractical for larger arrays, because the total number of subsequences grows exponentially, specifically 2n. This makes a brute force solution infeasible for large n, as it would require n*2 to the power of n computations. Instead, we need to find an optimized approach. By leveraging sorting and certain mathematical properties, we can achieve a solution with a time complexity of n log n, which is much more efficient. This optimized method will allow us to solve the problem within the given constraints, ensuring that the solution is computationally feasible even for the maximum input size. To solve this problem, we first considered two approaches. The brute force approach involves generating all possible subsequences of the array, calculating their widths, and summing them up. Here, a subsequence's width is defined as the difference between its maximum and minimum values. While this method might seem straightforward, it has significant drawbacks. Generating all subsequences requires exponential time since there are 2 to the power of n subsequences for an array of size n. Additionally, calculating the maximum and minimum for each subsequence takes linear time, leading to an overall time complexity of n*2 to the power of n. This makes the brute force approach impractical for larger arrays due to the sheer number of operations required. Recognizing this limitation, we turn to an optimized approach that leverages sorting and contribution analysis to compute the result more efficiently. The optimized approach focuses on determining how each element of the array contributes as both the maximum and minimum across all subsequences. Here's the key insight: if we sort the array, we can compute these contributions without explicitly generating subsequences. For an element at index I in the sorted array, it contributes as the maximum in all subsequences formed by itself and the elements to its left, and as the minimum in all subsequences formed by itself and the elements to its right. Mathematically, the contribution of an element as the maximum is given by multiplying the element by 2 raised to the power of its index, while its contribution as the minimum is determined by multiplying it by 2 raised to the power of n(i1). By summing these contributions for all elements, we can efficiently calculate the total sum of subsequence widths. This algorithm uses modular arithmetic to handle large numbers, ensuring correctness even for large inputs. Analyzing the complexity of the optimized approach reveals its efficiency. Sorting the array requires O, n log n, time, and iterating through the array to compute contributions takes O, n. This results in an overall time complexity of O, n log n, which is a significant improvement over the exponential complexity of the brute force method. This approach is not only efficient but also scalable for arrays with up to 10,000 elements. Furthermore, it avoids the overhead of explicitly generating subsequences, making it far more practical for real-world applications. Given these advantages, the optimized approach is the clear choice for solving this problem. It strikes a balance between computational efficiency and simplicity, ensuring that we can handle even the most challenging input sizes. While the optimized approach does not explicitly generate subsequences, this trade-off is acceptable because the problem only requires the sum of widths, not the subsequences themselves. Adding a sorting step introduces a pre-processing overhead, but this is outweighed by the dramatic reduction in overall runtime compared to the brute force method. In conclusion, the optimized approach, which combines sorting and contribution analysis, is the best strategy for this problem. It balances efficiency, correctness, and simplicity, making it not only scalable but also easy to implement. By focusing on the mathematical properties of subsequences, we achieve a clean and concise solution that meets the problem's requirements effectively. To begin, the problem asks us to calculate the sum of the widths of all possible subsequences of a given array. The width of a subsequence is simply the difference between its largest and smallest elements. A natural but naive approach to tackle this is the brute force method. Here, the idea is straightforward: generate every possible subsequence of the array, compute the width for each subsequence, and finally sum up all these widths. While this approach is not efficient, it provides a clear and systematic way to solve the problem by exhaustively considering all possibilities. The first step in this method is to generate the subsequences. This can be done using recursion or bit manipulation. For instance, if the array is 1, 2, the subsequences are 1, 2, and 1, 2. These represent all possible subsets of the array, including the empty one. Once we have the subsequences, the next task is to calculate the width for each. For a given subsequence, we determine the maximum and minimum elements, then compute the width as the difference between these two values. It's important to note that for subsequences containing a single element, the width will always be 0, since the maximum and minimum are the same. For example, in the subsequence 1, both the maximum and minimum are 1, so the width is 0. After calculating the width for each subsequence, we maintain a running total in a variable, say total_width, which starts at 0. For every subsequence, we add its width to this running total. Finally, once all subsequences have been processed, the value of total_width gives us the result, which is the sum of the widths of all subsequences. To make this process clearer, let's walk through an example with the array 1, 2, 3. First, we generate all subsequences 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3. Next, we calculate the widths for each subsequence. The empty subsequence is ignored since it does not contribute to the sum. For single-element subsequences like 1, 2, and 3, the width is 0. For 1, 2, the width is 2, 1 equals 1. Similarly, for 1, 3, the width is 3, 1 equals 2, and for 2, 3, it's 3, 2 equals 1. Lastly, for 1, 2, 3, the width is 3, 1 equals 2. Adding these up, the total width is 0 plus 0 plus 0 plus 1 plus 2 plus 1 plus 2 equals 6. Therefore, the result for this example is 6. While the brute force approach is easy to understand, it's important to recognize its limitations. The number of possible subsequences grows exponentially with the size of the array, following the formula 2^n. For small arrays, this may not be an issue, but for larger arrays, the computational cost becomes prohibitive. Additionally, there are edge cases to consider. For instance, an empty array results in a total width of 0 since there are no subsequences to process. Similarly, arrays with all identical elements, such as 2, 2, 2, will have widths of 0 for all subsequences because the maximum and minimum values are always the same. This exponential growth and the need to compute the max and min for every subsequence make the brute force approach highly inefficient, with a worst-case time complexity of 2 to the power of n*n. To implement the brute force method, we rely on some fundamental data structures. First, we use arrays to store both the input array and the subsequences. Arrays are ideal because they allow sequential access and efficient storage. Next, for generating the subsequences, we can use either recursive calls or a bitmask representation. Recursive functions utilize the call stack to explore all possible subsets of the array, while bitmasking leverages the binary representation of numbers to systematically represent each subset. Both approaches are valid, and the choice between them depends on the programmer's preference and the specific constraints of the problem. The brute force solution revolves around three key operations. First is the generation of subsequences, which can be done using recursive backtracking or bit manipulation. Second is the width calculation, where we identify the maximum and minimum values in each subsequence. Finally, we sum up these widths to get the total result. While this approach is conceptually simple, it is computationally infeasible for large arrays due to its exponential complexity. To address this inefficiency, optimized methods exist that use sorting and mathematical properties to reduce the computational complexity to n*log n. These optimizations make the problem solvable for much larger arrays in a reasonable amount of time. Here, we start by defining the Subsequence method inside our solution class. The first thing we do is define a constant mod with a value of 10 to the power of 9 plus 7 to ensure our calculations remain within modular arithmetic, preventing overflow for large inputs. We also calculate the length of the input list nums, which we'll use later. Next, we sort the input array. Sorting is essential because it guarantees that we can systematically process the elements in increasing order, which simplifies calculating the contributions of each element as both a maximum and a minimum in subsequences. After sorting, we pre-compute the powers of 2 up to n1, where n is the length of the list. These pre-computed powers help us determine the number of subsequences where each element contributes either as a maximum or as a minimum. The array powers _of_2 is initialized with ones, and we use a loop to populate it such that each entry represents 2 mod. This is efficient and avoids recalculating powers repeatedly during the main logic. Finally, we initialize the result variable to 0. This will store our running total of the sum of subsequence widths, which we compute in the following loop. The loop iterates through each element of the sorted array, and for every element, we calculate two types of contributions. First, the element's contribution is the maximum of subsequences, which is nums, I, *powers _of _2, I. Second, its contribution is the minimum of subsequences, which is nums, I, *powers _of _2, and I1. The difference between these two contributions is added to the result, and we use modulo arithmetic to ensure the result stays within bounds. Finally, after processing all the elements in the array, we return the computed result. This result represents the sum of widths of all subsequences, modulo 10 to the power of 9 plus 7. By leveraging the pre-computed powers of 2 and sorting the array, this implementation efficiently calculates the desired value in n log n time due to the sorting step, while the rest of the computation is linear. This approach ensures we account for every possible subsequence without explicitly generating them, making it both optimal and scalable for large inputs. Here we start by importing the required libraries and defining the Subsequence method. Inside the method, we declare a constant mod to handle large numbers using modulo arithmetic, and we store the length of the input array nums in the variable n. To ensure the subsequences are processed in a sorted order, we sort the input array using arrays.sort, nums. Next, we pre-compute the powers of 2 modulo mod and store them in an array called powers of 2. This helps us efficiently calculate the contribution of each element in the subsequences later. The first power of 2 is initialized as 1, and for each subsequent index, we calculate the next power of 2 by multiplying the previous value by 2 and taking the modulo mod. After this, we initialize a variable result to 0, which will store the final sum of subsequence widths. The next step is to iterate over the array and calculate the contributions of each element as both the maximum and minimum in all possible subsequences. For each element in the array, we calculate its contribution as the maximum element in subsequences by multiplying the element with the corresponding power of 2 from the precomputed powers of 2 array, and then taking modulo mod. Similarly, we calculate its contribution as the minimum element by using the power of 2 at the mirrored index from the end of the array. The difference between these two contributions is added to the result, ensuring that we maintain modulo arithmetic by adding mod before applying the modulo operation. Finally, the result is returned as an integer, representing the sum of widths of all subsequences modulo 10⁻9 plus 7. This approach ensures efficiency by leveraging sorting and precomputing powers of 2, allowing us to handle the constraints effectively. To solve the problem, we start with an example where nums is 2, 1, 3. The first step is to sort the array, which gives us 1, 2, 3. Sorting ensures that subsequences are processed in increasing order, which is critical for calculating contributions as maximum and minimum values. Next, we precompute the powers of 2 modulo 10 to the power of 9 plus 7, up to n1, where n is the size of the array. Here, n is 3, so we calculate powers of 2 as 1, 2, 4. These values will help us determine the number of subsequences where each element is either the maximum or the minimum. Now, we begin iterating through the sorted array. For the first element, nums 0 equals 1, its contribution as the maximum is 1 asterisk powers of 2, 0, which equals 1. Its contribution as the minimum is 1 asterisk powers of 2, 2, which equals 4. These contributions will be used to update the result, as we'll see next. For nums 0 equals 1, we subtract its contribution as the minimum from its contribution as the maximum. 1 to 4, mod 10 to the power of 9 plus 7 equals minus 3 mod 10 to the power of 9 plus 7, which wraps around to 100, 0000004. This becomes our initial result. Moving to nums 1 equals 2, its contribution as the maximum is 4, and as the minimum, it is also 4. The difference here is 0, so the result remains unchanged at 100, 0000004. Finally, for nums 2 equals 3, its contribution as the maximum is 12, while its contribution as the minimum is 3. The difference, 12 to 3, equals 9. Adding this to our result gives 100,000,004 plus 9, mod 10 to the power of 9 plus 7, which simplifies to 6. Thus, the final output for this example is 6. In the second example, nums is 4, 7, 2. We start by sorting the array, which gives 2, 4, 7. Sorting ensures we can systematically process contributions for all subsequences. Next, we precompute the powers of 2 modulo 10 to the power of 9 plus 7, resulting in 1, 2, 4, just as before. Now, iterating through the array, for nums 0 equals 2, its contribution as the maximum is 2 asterisk powers of 2, 0, which equals 2. As the minimum, its contribution is 2 asterisk powers of 2, 2, which equals 8. The difference, 2 to 8, gives minus 6 mod 10 to the power of 9 plus 7, which wraps around to 100, 0000001. This becomes our starting result for this example. For nums 1 equals 4, its contribution as the maximum is 8, and as the minimum, it is also 8. The difference, 8 to 8, is 0, so the result remains 100, 0000001. Then, for nums 2 equals 7, its contribution as the maximum is 28, while its contribution as the minimum is 7. The difference, 28 to 7, equals 21. Adding this to the current result gives 100,000,00001 plus 21, mod 10 to the power of 9 plus 7, which simplifies to 15. Thus, the final output for this example is 15. In the third example, nums is 1, 1, 1. Sorting the array doesn't change it, so it remains 1, 1, 1. As before, we precompute the powers of 2 modulo 10 to the power of 9 plus 7, resulting in 1, 2, 4. Now, we process each element. For nums 0 equals 1, its contribution as the maximum is 1, and as the minimum, it is 4. The difference, 1 to 4, equals minus 3 mod 10 to the power of 9 plus 7, which wraps around to 100, 0000004. This becomes our initial result for this example. Moving on to nums, 1 equals 1, we calculate its contributions next. For nums, 1 equals 1, its contribution as the maximum is 2, and as the minimum, it is also 2. The difference, 2 to 2, is 0, so the result remains 100, 000,0004. Finally, for nums, 2 equals 1, its contribution as the maximum is 4, while its contribution as the minimum is 1. The difference, 4 to 1, equals 3. Adding this to the current result gives 100,000,0004 plus 3, mod 10 to the power of 9 plus 7, which simplifies to 0. Thus, the final output for this example is 0. Here, we analyze the time complexity of the given solution, which is O, n log n, overall. This complexity arises from three key components. First, we have the sorting of the input array nums, which is done using Python sort method. Sorting an array of size n takes O, n log n, time, as it is the dominant operation in this step. Second, we pre-compute the powers of 2 modulo mod, which involves iterating from 1 to n1. Since each iteration involves constant time operations like modulo arithmetic, this step has a time complexity of O, n. Lastly, in the main loop, we iterate through the array to compute the result. For each element, we calculate two contributions, one as the maximum and the other as the minimum, and update the result. This computation is also performed in constant time per iteration, leading to a time complexity of O, n, for this step. These components together define the overall time complexity. Now, let's combine the time complexity of the individual components. Sorting contributes O, n log n, pre-computing the powers of 2 takes O, n, and the iteration for result computation also takes O, n. Since O, n log n, dominates O, n, the overall time complexity of the solution is O, n log n. Moving on to the space complexity, the solution requires O, n, space overall. First, the input array nums itself takes O, n, space. Importantly, Python sort method uses timsort, which is an in-place algorithm, so no additional space is needed for sorting. Second, the powers _of _2 array stores n values, each corresponding to a power of 2 modulo mod, contributing another O, n, to the space complexity. Additionally, we need to consider auxiliary variables such as mod, n, result, contribution _max, and contribution _min. These are scalar variables, meaning they require only O1 space. When we combine these factors, the space complexity is dominated by the powers _of _2 array, which takes O, n, space. Comparing this optimized approach to a naive solution helps highlight the efficiency of our method. In a naive approach, we would generate all possible subsequences of the array. Since an array of size n has 2 n subsequences, this approach would have a time complexity of O2 to the power of n. Calculating the width of each subsequence and summing them would require exponential time, and the space complexity would also be O2 to the power of n, to store these subsequences. By contrast, the optimized approach avoids generating subsequences explicitly and instead leverages mathematical properties, reducing the time complexity to O, n log n, and the space complexity to O, n, making it far more efficient. Finally, let's solidify the time complexity analysis with a mathematical proof. Sorting an array of size n using timsort, the algorithm used by Python sort method, requires O, n log n, comparisons and swaps in the worst case. This is the dominant step in our solution. The computation of the result involves iterating through the array and, for each element, calculating its contribution as both a maximum and a minimum in constant time. Since there are n elements, this step has a time complexity of O, n. Combining these, the overall time complexity is determined by the sorting step, which is O, n log n. By optimizing both the time and space complexities, this solution achieves significant improvements over the naive approach, making it suitable for larger input sizes. Let's start by discussing some common mistakes that can occur when solving this problem. First, not handling edge cases for an empty or single element array is a frequent oversight. If the array is empty, there are no subsequences to consider, and if it contains only one element, the width is always 0. Neglecting to explicitly account for these scenarios can lead to runtime errors or incorrect results. Next, an inefficient brute force implementation is another common issue. Trying to generate all possible subsequences results in exponential time complexity, which quickly becomes impractical for larger arrays and often leads to time limit exceeded errors. Lastly, incorrect calculation of the width is another pitfall. It's crucial to remember that the width is defined as the difference between the maximum and minimum values in a subsequence. If the subsequence isn't sorted, subtracting the first and last elements directly might yield the wrong result. Always ensure the calculation respects this definition. Now, let's explore a few additional challenges. Misunderstanding the problem constraints is a critical mistake. For instance, overlooking limits on array size or the range of element values can lead to incorrect assumptions about the solution's feasibility or precision requirements. Another common error is overlooking modular arithmetic when working with large numbers. If the result needs to be computed modulo a constant like 10⁻9 plus 7, failing to apply modular arithmetic can result in integer overflow or incorrect results. Additionally, in interviews, there are some important insights to keep in mind. Many problems involving subsequences or subsets share similar patterns, such as sorting the array and using mathematical properties to optimize the solution. Modular arithmetic is also a recurring theme, so be prepared to explain its role and benefits. Finally, clear communication is key. When proposing an optimized approach, clearly outline why the naive brute force method is inefficient and describe your thought process in transitioning to an improved solution. To deepen your understanding, let's look at related problems that share concepts with this one. Examples include LeetCode 898, which deals with bitwise ORs of subarrays, and LeetCode 910, which focuses on minimizing the range of an array under constraints. There's also LeetCode 198, the classic house robber problem, and LeetCode 491, which involves finding all increasing subsequences. These problems highlight the versatility of the techniques we've discussed. Now, when it comes to alternative approaches, the sorting-based strategy is a popular choice. By sorting the array, you can efficiently calculate each element's contribution to the sum of subsequence widths based on its position as either the minimum or maximum in different subsequences. This method has a time complexity of O(n log n) due to sorting, making it suitable for larger arrays, though it may require additional space for sorting. Another option is the dynamic programming approach, which pre-computes results for subsequences of various lengths. While it's more intuitive for smaller cases, its higher time and space complexity, often O(n squared), or worse, makes it less practical for larger inputs. Finally, let's discuss mathematical optimization using powers of 2. This approach leverages the fact that each element's contribution as the minimum or maximum and subsequences can be determined by pre-computing powers of 2. After sorting the array, you can calculate how many subsequences each element contributes to, both as the smallest and the largest value. This method is extremely efficient, with a time complexity of O(n) after the sorting step. However, it requires a solid understanding of combinatorics to implement correctly. The trade-off here is that while the approach is highly optimized for large inputs, it demands a bit more mathematical insight compared to other methods. By mastering this technique, you can tackle even the most demanding variations of this problem with confidence. Great job! We've reviewed the key aspects of solving problem number 891, sum of subsequence widths. Remember the importance of subsequences, optimization strategies, and modular arithmetic. Keep practicing and exploring more challenging problems. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!